Okay, time to get started. Looks like we're recording. Okay, so last time we finished section 1.6. Moving on now to 1.1, because I do these out of order, at least out of the book's order. Very little to say about 1.1, honestly. It's mostly stuff that I think y'all should have already seen. So again, you got to keep in mind, I have to make these tough choices of what to spend class time on. I think y'all can mostly read section 1.1. So I do want to point out specifically, though, that the book uses bold to indicate something as a vector. I prefer to put the little vector arrow, little hat thing on top of the name to indicate that it's a vector. I suppose it's arbitrary, but it just seems to me that when you're handwriting, bold is kind of, how would you do that, right? It seems strange and tedious. The vector hat makes sense and more, it's just easier and faster. So I will always use the vector hat myself. Another notational observation. This vector right here, represented by this arrow between those 2 points. The book refers to that like so. I guess that's fine. It goes from P1 to P2. Okay, so that makes sense, I guess. I'll point out, though, you can also view this as P2 minus P1, keeping in mind that P2, being as it is a point, but don't forget points can also be thought of as vectors. By the natural correspondence between points and vectors. And likewise, P1 can be thought of as a vector, even though it's, perhaps more naturally viewed as a point. And so writing these all as vectors, this green vector is literally P2 minus P1, right? So we have these two different choices between, how we're going to represent this thing, and I would like to make my pitch for why I like this second notation better. And the reason why is I like algebra. Algebra is a good thing. Algebra is a tool that we can use to solve problems. If there is algebra in what we're talking about, I want to see it, right? Because then that's something I can actually do algebra with. Right? And if you write it like this, technically there's a minus sign in there, but you can't see it. So you can't see it, you can't do anything with it, right? So I want to encourage you to think in these terms right here, and to tolerate that the book will write it like this, but to do it this way yourself. Okay. Does that make sense to everybody? Is everybody happy? Okay. That's section 1.1. So now on to section 1.2. Again, a bunch of stuff that I'm not going to talk about because tough choices. I am, however, going to spend a bunch of time talking about parameterizations because this is something that I think y'all probably haven't seen, or at least many of you haven't seen, and it is not only a new idea, but also I don't want to say challenging, but it's something that requires sort of thinking through, and it's going to be really important in the class. So I think it deserves a bunch of class time. So here we go. What a parameterization is. It gives position as a function of, I'm going to say time. Position is a function of time. Okay, now let me correct myself. Technically, you can use any single parameter. So you could have position as a function of Q if you want, right? Doesn't really matter. But if you think of it as time, position as a function of time, for every time you're at a certain location, as time passes, that then draws out the curve. And so viewing the parameter as time, you can think of the parameterization literally as drawing the curve. Or think of it as a description of a little movie that traces out the curve. So, example. Let's see here. Here we go. This right here is a parameterization because it gives us position, right? X and Y coordinates, that's position in the plane, as functions of time. Right? X is a function of time, Y is a function of time, therefore position is a function of time. Everybody good so far? All right. So that is a parameterization. Now, next question, how do we get some idea of what specifically is this parametric curve? What is this tracing out, right? What does it look like? And what I like to do here is start by just making the appeal. Let's see, I want to give myself some more space. Here we go. That if we know x and y as functions of time, we can just plot a bunch of points. So for example, plug in t equals 0. That gives you a spot. Gives you 1, 0 in this case. Plug in a slightly larger value of t. That's going to make cosine a little smaller. It's going to make sine somewhat larger. That would give you a point, let's say, about right there. And you can literally just keep plugging in numbers. You'll notice I'm not going to actually do this. But if you were to continue to plug in numbers, what you would find is that it is cruising along kind of like that. And so this formula right here, position as a function of time, is tracing out a curve kind of like that. Everybody okay with that? All right, now it kind of looks like it's making a circle. Again, I'm not going to talk about the arithmetic of the particular points, but if you were, you would find that it's kind of looping back around on itself. We could even speculate that maybe this is a circle. So how do we decide if this is a circle? Well, keep in mind, we have explicit formulas for x and y. And notice that since x is cosine and y is sine, looking for a relationship between x and y boils down to, can I think of a relationship between cosine and sine? And we all, of course, remember, oh, and I forgot to fill that in, there is a convenient, easy relationship between cosine and sine, and that is the Pythagorean identity. We know that cosine squared plus sine squared is 1. And that means that every point on this parameterization satisfies this equation. Let me say that differently. Every point that comes out of this parameterization is on this unit circle. So yes, in fact, this is literally tracing out the unit circle as we would have suspected from plugging in actual numbers. How about that? Everybody good? All right, so sometimes you get lucky. We got lucky here because we just happened to notice a convenient algebraic relationship. Just, oh my gosh, I totally remember. There's that convenient relationship. What do you do if you don't get lucky? Here's another parameterization, different parameterization. Different notation, right? Notice I didn't say x equals and y equals. I say, look, position x is this formula. Keep in mind when it's written like this, don't forget an ordered pair means that the first one is your x coordinate. So that t minus 1 is x. And this 3t plus 4 is your y. So, okay, do I see any obvious algebraic relationship there? Well, oh gosh, I mean, maybe. I mean, they're both degree 1 polynomials of t. I guess I noticed that, right? But it's not, I mean, there's some details that I'm going to have to kind of deal with. So how do you find that actual algebraic relationship? Here's how I like to do it. Correction, here is one of the ways I like to do it. Let's see, I'll use red. Step 1, solve for t in one of the equations. Step 2, keeping in mind that the other coordinate is telling you your formula for y, plug in your newfound formula for t into the second equation. Right, and in doing so, this 3t plus 4, well, that t becomes x plus 1, as previously solved. And now all together, notice I have a relationship between x and y. Specifically, y is equal to all of this stuff, but you can kind of multiply and collect terms, and in conclusion, y is related to x, like so. Everybody see the process? Solve for t in one equation, plug it into the other. So that works sometimes. And what we've accomplished there is we have turned a parameterization into an equation. Or you might say we've recognized what this is parameterizing because we've rewritten it as something that we recognize, right? We know this is a line. Okay. All right. Now, same question. Different solution. And before I show you the details, I want to point out this is going to happen a lot in this class. There isn't just one single way to answer a math question. There can be different approaches that have their advantages in different circumstances, right? So this example that I'm using is convenient for this first approach, and it's also pretty convenient for this second approach. But in other cases, one or the other of these might be more convenient than the other. So don't view this as an either or, take your pick. View this as you need to understand both of these, because depending on the circumstance, who knows which one of these you might really need. So let's dive into the second one. Here we go. Again, don't forget, that's x and that's y. So what I'm going to do is I'm going to take the formula for x and ask, what do I have to do to this formula for x to turn it into the formula for y? What is this algebraic process that turns this into that? And in this case, it's not that bad. I mean, again, previously observed, I have a degree 1 polynomial in t. I have another degree 1 polynomial in t. I just have to, in this case, multiply by 3, add 7, right? And that turns this little expression into that expression. Or you might say it creates a relationship between x and y. And notice it's the same relationship that we got doing it the other way. So again, pros and cons. Now let me point out, when will one of these be better than the other? Here in this first method, I have to solve for t in this expression. Now that was easy here. But what if this first coordinate formula was a quintic polynomial? Then you can't solve for t. And this becomes a bad method up here, right? Not very helpful. What if this formula for x and this formula for y just don't seem to have any clear relationships? What if the formula for x is like, sinusoidal, but the formula for y is like some weird combination of exponentials and logs? I don't know how to turn the one into the other. That this becomes not very useful. So either of those cases, the other method might be the one you want to use. Does that make sense to everybody? So I don't like to think of this as here's how you do them. I like to think of this as I show you tools, and then you identify, depending on the circumstance that you're in, what kind of a tool do I need? Sometimes you need a hammer, sometimes you need a screwdriver. They're pretty different scenarios, right? So tools for your toolbox is a metaphor that I use a lot. Okay, let's see here. Oh, how am I doing on charge? I think I'm probably good. Let me get this charging cable. Okay. All right. Here's another parameterization to understand. Notice this has 3 coordinates, so this is a curve in space, curve in R3. Well, how would I understand a curve in R3? In this case, what I think is the best method is to kind of look at what I'm going to call projections. So in particular, if I say, let's just project vertically downward into the XY plane. ignore z, throw away the z coordinate. Look only at the x and the y. Well, here they are. There's x and y. Yeah. So this isn't going to help me understand the actual curve, at least not immediately, but it is going to tell me what you might say what the shadow is doing down in the xy plane. And how can I understand this shadow? Well, I've got the formulas here for x and y. I just need to understand what these formulas for x and y are doing. And lucky break, we happen to recognize this one. This is our first example a page ago. Right? So we already know, by the way, this happens a lot. There are certain curves that the parameterizations you should just be on the lookout for, and this is one of them. So make sure that you're really comfortable with the idea that this is a parameterization of the unit circle. We're going to see this all the time. Okay, so cool. I still don't know what my curve looks like, but I know that its shadow in the xy plane is going around in a circle. All right, next observation. Let's project to the z-axis. In other words, let's look just at the z-coordinate. All right, well, I mean, there's only one coordinate here. There's no sort of curve to keep track of, but I mean, we can ask the simple question of how is this z-coordinate behaving? And this is a pretty simple story. As t increases, as time passes, in other words, as we trace out this curve, well, this z-coordinate is just increasing with time. Right, so easy story. And so now what I'm going to try to do is to take these two observations, that the xy projection is a circle, that the z projection is, well, it's just kind of moving upward at a constant rate. I'm going to take these two observations together to understand the entire parametric curve. It's something that, this is hard to do, but the projection, the shadow is doing this, and then the height is doing that. And geometric appeal. It's a corkscrew, more commonly known in math circles as a helix. Everybody see that? Well, there's a certain amount of sort of geometric intuition, sense of what, just using your sense of geometry to kind of put these two observations together to draw this conclusion. Cool. All right. Now, the examples we've seen so far, I guess we've seen 3 examples so far. We started with the parameterization, given. And then we asked, what is the curve that this parameterization is describing? What we're going to do now is turn it around. We're going to say, suppose I know something about a curve, whatever that may be that we know. Can I figure out a parameterization? Can I create a parameterization? Or as we say, can we parameterize? Which just means to create a parameterization. Okay, and this is another skill that we're going to need. We're going to need to be able to create parameterizations of things that aren't already. So here is my favorite tool for this. This is called the graph parameterization. It's a really simple tool, very powerful, easy to use. Doesn't always apply, but when it applies, it's just awesome. And here's the idea. Very importantly, notice it only works if you have a graph. Namely, if one of the variables is a function of the other. It's very important. One of the variables is a function of the other. We'll talk more about what graphs are at a later date. For the moment, one of the variables is a function of the other. So here we're lucky. We're looking at y equals f of x. Y is the one variable that is, in fact, a function of the other. Then here's the trick. If you have a graph, let your parameter be the input variable. That's all there is to it. Everything's just going to work out. It's kind of awesome how nice this works. If you have a graph, let t be the input variable. Here we go. Let's do one. Let's take this curve right here. Hey, cool, we have a graph. We have y equals. More to the point, we have one of the variables equals a function of the other. So I'm going to follow the rule. I'm going to let t be the input variable. That input variable is x, so I'm going to let t equal to x. Notice that already kind of gives me half of my parameterization already. That one choice. And then notice furthermore, though, if x is t, you plug that in, and that pretty much forces y to be t squared. And we're done. We have our parameterization. We have position as a function of time. X and y explicitly as functions of time. So this works for any graph. Totally awesome. One step, basically. Right? Easy to use. Pretty nice method. Everybody happy? All right. Now, this first example I had set up with algebraically that y was the variable that was a function of the other being x, right? So I had exactly the same rules. There's no magic, alphabetical order. Doesn't have to. It's kind of arbitrary. It doesn't matter which variable is a function of the other. It doesn't even matter that your equation is even written as a graph. It just has to be that you can rewrite it as a graph. So notice here, for example, this is not written as a graph. This is not y equals a function of x. This is not x equals a function of y. And I can't solve for y, but I can solve for x. So solving for x, I got to, in other words, do a little bit of algebra. Rewriting it, in other words, as a graph. Okay, well, cool. Now I have a graph. I can use the graph parameterization. The big trick, recall, is that the input variable, now in this case, the input variable is y. Let t be that input variable. So now it's y that gets set equal to t. And again, kind of game over, because if y is equal to t, then that kind of forces x to be that. And again, we win. This equation that we started with, we now have a parameterization of it because we've got position as a function of t. What do you think? Everybody good? Cool. All right, this next example, a little weird. It's a good exercise, though. This is an example of a big strategy, a tool for your toolbox, as it were, of using vectors, in particular vector algebra. In particular, try to figure out how the thing that you're interested in is a sum of simpler things. And that's going to be the big, powerful tool that makes this all come together. There's a lot of little details, and we'll talk about the details. But try to figure out how to write the thing you're interested in as a sum of simpler things. And so here's the problem. We have a bicycle wheel here. I like to think of it as a bicycle wheel. And there's a reflector, as is very often the case, down at the, sort of at the edge of the wheel, where the rubber is. Right? And now imagine what happens as this wheel rolls down the road. And I think y'all have probably all seen this, that if you, like at night or at dusk or whatever, if somebody's riding a bicycle sort of, perpendicular to you, that reflector will catch the light from the street lamps or whatever, and it'll make this kind of scallopy, kind of sawtooth, jumpy sort of a pattern, right? Has everybody seen that, right? So this is what we're going to try to parameterize. Why are we going to parameterize it? Why don't we just write down an equation for it? And, well, it's going to turn out that if you try to write down an equation, it's prohibitively difficult, if even possible. I don't know how to do it myself. It's really hard to write as an equation. So we're going to try to find a better way to describe this curve. And parameterizing is going to be the trick. So per my previous note about how to approach this, notice that I can view that location, the location of the reflector at some arbitrary time. I can view that as a sum of simpler things. I can view that as a sum of the axle's location plus this difference vector that I'm going to call D. Right? So orange is blue plus purple. Yeah? Okay, so I claim this is a sum of simpler things. How do I know these things are simpler? Well, just real quick, I mean, just a rough appeal. The axle is not doing any sort of jerky motion at all. The axle just rolls in a straight line, right? Because it's a wheel has a fixed radius, and so the height of the axle above the road is always whatever that radius is, A apparent. So it's just nice straight line, really easy to deal with. Isn't that cool? And now let's talk about this difference vector, this purple difference vector there. And to keep in mind, it's a vector. We represent vectors with arrows, but arrows I have to draw in a location, but don't forget, vectors don't have a location. Vectors are just a direction and a magnitude, and you can draw them wherever you want. And just for convenience, I'm gonna come back to those details in a second, but I'm gonna draw it here. And as this wheel rolls, that purple D vector just kind of goes around in a circle. And we'll get to the details in a second, but describing something going around in a circle is not that hard. And describing something moving in a straight line, not that hard. Right? And so what I have here then is a pretty fantastic strategy by which I'm going to take the blue axle. Let me clean up my mess. I'm going to take the blue axle, which again we're not going to have much trouble writing down. We're going to take this purple D vector, just going around in a circle. That's not going to be that bad either. And the sum will give me this weird reflector motion that would otherwise be so hard to describe. Everybody see the big picture? Okay. All right, now before I get started, one other detail I want to talk about, and that is what is going to be our parameter. We need position as a function of a parameter. I am going to think of the parameter as being time, but what on this picture do I want to make it equal to? And you have a lot of choices here. If you wanted to, you could view this distance here, how far has the bike rolled. That would be a reasonable choice for your parameter. Various other choices you can make. I'm going to choose, as you'll see here in this picture, I'm going to choose this angle as drawn there, namely measured clockwise from the downward direction. And the reason I'm going to choose that particular angle measured in that particular way is because that angle is 0 where I'm starting, and it increases as the wheel rolls. And I feel like that's what time ought to do, right? Time, if you were to start a stopwatch, time would be 0 here, and it would be increasing as the wheel rolls. So, arbitrary choice, but that'll do it. Is that all right? Yep.
If you have an arbitrary graph, what would you say would be like the best parameterization?
Yeah, that's too general of a question. Yeah, it'd be nice if there was a single answer that sort of always, do this or always do that. But yeah, every question's just different, and so it's I can't give you a crisp answer to that. So you're going to have to let circumstances kind of be your guide. I'll say what I think is particularly convenient about this angle T in this case is that you'll see in a moment that angles are going to be relevant, and you'll also notice that distances are going to be relevant. And when you need to make relationships between angles and distances, trig shows up, and then you have to ask, Do you want to write distances in terms of angles, in which case you write down trig? Or do you want to write angles in terms of distances, which means you have to deal with inverse trig? And given my choice, I'll take trig every time. Right? So I'm choosing the angle in the hopes that I can avoid inverse trig functions. Does that make sense?
Yeah.
Cool. All right. Alrighty, so let's talk about the details of the axle. The axle being right here, we've already made this observation that the height is A. Cool, nothing to it. That means the y coordinate of the axle always A. No problem. Okay, now what about, though, the x coordinate? And there's a really clever physical observation to be made here. That x coordinate, you will notice, is the amount of road that has touched rubber between the start of the rolling and the current state of the wheel. So the x-coordinate is the amount of road that has touched rubber. And now I physical appeal, that the amount of road that has touched rubber has to equal to the amount of rubber that has touched road. That's how wheels work, right? I hope y'all got some physical intuition for that. If you're not entirely comfortable with that, you can talk to me after class. I'll, draw some pictures or something. But the amount of rubber that's touched road, the amount of road that's touched rubber have to be the same. Yeah.
So is t the angle from the vertical to the p vector?
Yeah, t is this angle. It's let's see here. It is measured from starting from straight down, measured going counterclockwise until you get to the direction of the p vector. That's right. Is that cool? Okay. All right. Okay, so with this observation being made, if I want to know this blue x-coordinate, well, that's the amount of road that's touched rubber. That's the amount of rubber that's touched road. And this is an arc of a circle of radius A, an angle T. And we have an easy formula for the length of an arc of a circle. It's radius times angle, so A times T. So, nothing to it. And we have parametrized now. Let's see here. We have parametrized, our axle. And I'll do it here. Our axle parametrized like so. Everybody happy? All right, now next, let's talk about this D vector. What's the deal with that D vector? Easy observation to make about the D vector is this right here. It's a vector known magnitude A, and if I were to know this angle theta, then D is just A cosine theta, A sine theta, right? So that's flashbacks to high school trig, right? That you can make a little triangle if you like, but those x and y coordinates, a little bit of high school trig, A cosine theta, A sine theta. Is everybody happy with that? Now we're not done yet, but does everybody see that part at least? And here's the problem. I've got D written as a function of theta. I have A written as a function of T. I need to add them up, and I need them all to be in terms of a single parameter. So I'm going to have to figure out how to eliminate theta. I'm going to need to figure out how to write theta in terms of T so I can plug in and get rid of it. And the observation to make is that theta and T, which you see right here, notice that they always add up to 3 pi over 2. Right? As T gets bigger, theta gets smaller. And so the sum is always 3 pi over 2. Everybody happy? Okay. Well, if the sum is 3 pi over 2, then there's our formula for theta. Theta is 3 pi over 2 minus T. And you can take that formula for theta and plug it into right there. And notice that means D is going to be a formula involving cosine and sine of a difference of two angles, and I hope you all recall that there are these things called angle addition formulas. I know that a lot of you don't know the angle addition formulas, at least not by heart, but this is a really useful thing to know, and using those angle addition formulas, you can rewrite D in terms of T, like so. So let me make a note down here. You do need to make sure that you learn these angle addition formulas, cosine of A plus B and sine of A plus B. So look them up in your old trig books, or if you don't have those, I assume they're easily Googleable, right? But you do need to know these formulas going forward. Is that cool? Everybody on board? You'd be surprised. They just come up a lot, and high schools make choices about what to require students to know based on sort of the average student in the high school class, and maybe that's a reasonable choice in that context. But in this multivariable calculus class, we're gonna need these formulas. Okay. All right. So game over, and we win. And just to sort of put it all together real quick. Let's see here. A was that, which is here, and D is that, which is here, and therefore our reflector is this formula right here. So a lot of details. Try not to get lost in the details. The big moral here is that sometimes hard to describe things are the sum of simpler described things. Deal with the simpler things and then add up when you're done. Okay. All righty. Here's another one. How to parameterize a line. Now it's again, if you just at a glance you look at a line like this, how would I write a formula for position as a function of time? You can see how it might be unclear exactly how to proceed. But again, I can write a point on this line very simply as a sum of simpler things. Now, before I get to those details, we do have to talk about what line this is. I'm going to assume that I am given, or that I can find, by whatever means, a point on the line. We're going to need that. And I'm going to need a vector parallel to the line. We're going to need that. So if those are given, check it out. This arbitrary point x on the line, I can write as being x naught plus, some vector parallel to the line. But wait a minute, I already have a vector parallel to the line. This dark green vector, it's just going to be some scalar multiple of this light green vector. And a scalar multiple would just mean it's some parameter t times that light green v. And so altogether then, blue plus dark green gives me orange, gives me the point on the line that I'm trying to describe. Everybody on board? No? Not happy?
How'd you get a TV?
Well, so this vector here that I add to x naught to get x, right? I mean, if I've got a point on the line, and if I want a different point on the line, I need to add a vector parallel to the line. And then I just make the observation, well, this is parallel. That means it's a multiple of this. And so I'm just going to let, whatever that multiple is, I'm just going to call it t. Yeah. And then as t increases, this point will just, this green vector will get longer and longer. Therefore, this point will just move further and further along the line. Is that satisfying?
Yeah.
Okay. Cool. Yeah.
What does it mean if there's a line on a vector plane?
I'm having trouble hearing you. I'm sorry.
Sorry. What does it mean if there's just a line on a vector plane? Is it a vector as well, or it can be classified as a line?
So a line is a set of points, right? A vector is arguably a point, right? So geometric object in general is typically made up of a bunch of points. So it would be a mistake to try to describe a line as being a vector, because they're different kinds of things. A line is a bunch of points. Do you see the difference? I'm not sure if I answered your question. Yeah? Okay, okay, cool. Feel free to ask me after class if you like. Okay. All right. Okay, moving along. Where are we? Here we go. Here's another nice trick. Sometimes you get lucky. It's always good to be on the lookout for what I'm going to call freebies. Maybe an overstatement, but sometimes what you want to parameterize is very similar to something you've already parameterized. And then you don't have to kind of reinvent the wheel. You can just kind of tweak what you've already got, and boom, you're done. So here's a great example. Let's take this ellipse with this equation here. And I assume y'all are good with all of your Algebra 2 and you know how this thing works. Everybody comfortable that this is an ellipse? All right. Important thing to remember. An ellipse is a deformed circle. So an ellipse, I know, again, this is just an old fact of high school. An ellipse is what you get when you take the unit circle and you stretch horizontally by some amount, and then you stretch vertically by some amount. So I know for sure that this ellipse, if I knew how to parameterize this circle, I could just kind of stretch accordingly and parameterize my ellipse. Well, good news. I do know how to parameterize our circle. Again, our old friend, right? We've seen this several times now, and we're going to see it many more. So that is an existing parameterization. And now I just have to figure out how to deform it. How do I need to tweak this parameterization to get what I want? Well, real quick case, this 3 here tells you that coordinate is 3, and that tells me that I need to stretch by a factor of 3 in the x direction. Now, how am I going to stretch by a factor of 3? Well, my existing parameterization of cosine and sine, I'm going to stretch by a factor of 3 horizontally by multiplying by 3 in the x-coordinate. Now all my x-coordinates are 3 times bigger. I have stretched by a factor of 3. Yeah? Likewise, this 2 right there tells me that coordinate is 2. That tells me I need to stretch vertically by a factor of 2, in which case I multiply all the y-coordinates by 2, which, again, easy to do. So all together then, my ellipse is parameterized by something that started off with the unit circle, and then I just deformed it appropriately. Everybody happy? Now, this is just one example. It's not that every deformation that you're going to see is necessarily going to be stretches. It might be that the deformation is that, well, you had a circle here and you want a circle over here. And here you're not really stretching, you're just kind of sliding things over. Who knows, right? You may reflect, or there's a lot of different kinds of deformations that you might want to do. But this is just an example of if you start with something that you understand, and you understand the relationship between what you have and what you want, then a deformation is on the table. Something you can figure out how to make work. Yeah?
If it's instead of x over 3, it's something like maybe like x minus 2 or like x plus 1.
Yeah, then that's going to be translations instead of stretches. Yeah. So yeah, there's a bazillion examples, but yeah, that something analogous to this. Yeah, right. Is that cool?
Yeah.
Okay. Everybody happy? Okay. All right. Okay. Here is a point of view about parameterizations and equations. I think it's important to recognize that they're different things. Now, they have something in common. A parameterization is an algebraic thing that helps you understand a curve. An equation is an algebraic thing that helps you understand a curve. Yeah, so they play similar roles in a way, but there's some big differences. The main difference, as I see it, a parameterization generates points. You plug in a value of t and out comes a point on the curve. It literally generates points. Whereas, by contrast, that is not what equations do. Equations don't generate points. If you think about it, an equation is just algebra equals other algebra. You can plug points into it. You can see if the equation works or not, but it doesn't make points for you, at least not intrinsically. Right? So an equation tests points. Again, you give me a point, you can then put that into an equation. And again, either it works or it doesn't. And correspondingly, that point either is or isn't on the curve. Okay, so very different objects. Now, one of the reasons I mentioned this is to explain a quibble that I have. Some books will refer to a parameterization as parametric equations. And it really bugs me because, again, really importantly, these are different things. Why would we use the same word in reference to two importantly different things, right? It is really bugs me. Anyway, so be prepared. You're going to hear the phrase parametric equations, and just don't fall for it. Parameterization isn't fundamentally performing the same role that an equation is. Okay, the other reason I want to point this out is that you can kind of see how the Legos fit together in a sense. A parameterization produces points. Those points, conceivably, that you could test with the equation, and that's exactly how we're going to deal with this question. We have a parametric curve. We have an equation, which we will eventually learn in the next few class meetings. It turns out this is a plane. We'll worry about why that is later. Don't worry about that for the moment. We have a curve. We have an equation, which, again, happens to be a plane. Where do they intersect? What points on this curve are also on this plane? And the approach is pretty straightforward. I'm going to use the parameterization to generate points, and then I'm going to test them. Right? So for whatever value of t, this is the generated point from my parameterization. And the action of testing this generated point is to take these x, y, and z, plug them into my equation, and then ask, did it work? Everybody see what I'm doing there? So a little bit of algebra ensues, no big deal. Easy to do this algebra, and the punchline is t can be either plus or minus 1. Cool. What does that tell us? That isn't actually what we were asked. You'll notice we were asked, what's the points? We have found the t values. The question was to find the points. I have the t, I want the points. Well, the parameterization is what allows me to turn a value of t into the corresponding point. So the last little bit at the end, you plug into the parameterization, these values of t into the parameterization, and there you go. Okay. All right, last thing I'm going to talk about, and then I think we're going to run out of time. How do you turn a parameterization into some sort of a point tester? Now, we're going to do this specifically for a line. So here's a parametric line. This is a point generator. You come to me with any value of t, it doesn't even matter. I can plug into this algebra right here, and bam, out comes a point that's definitely on my line. This is a point generator. But how would I make a point tester? How would I, you come to me with a point, x, y, z. how do I decide if that point is on this line? What am I going to start plugging in values of t and just keep plugging in values of t and fingers crossed I hope that I accidentally generate the exact point that you want to know if it's on the line? This is not a good approach. Right? So the idea that I would look for a value of t that happens to generate exactly the right point is silly. All right, but here's what you can do. Clever move. Notice that this one equation here, vector equation, only works if all three coordinates work. So this is actually three equations. And in each of those three equations you can solve for t. So this t, looking at the first coordinate, that t has to be x minus x naught over a. Looking at the second coordinate, it has to be y minus y naught over b. It also likewise has to be z minus z naught over c. So now let me rephrase the question then, right? With the understanding that this algebra is the same as this algebra, is there a value of t that's equal to this and that all at the same time? Now that seems like a big ask. How could one number t equal to three things? Is there a value of t that's equal to 2 and 7 and 9? No, come on, that's crazy. But is there a value of t that's equal to 4 and 4 and 4? Yeah, sure there is. T is 4, right? It becomes ridiculous. Right? So the punchline then is the only way that there can be a value of t that's simultaneously equal to all three of these things is if all three of these things are equal to each other. And that's your point tester. You come to me with a point x, y, z. I'll say, well, hey, compute all three of these things. If they're all equal to each other, then yes, that point is on your line. Yes?
I just want to ask, what was that first symbol again with the t?
Yeah, I'm sorry. I know this notation is hard to get sort of used to. This means there exists or there is. And this little weird symbol here means such that or so that. So what this is asking, does there exist a value of t for which, so that this equation, is there a value of t that makes this work? Yeah. Okay, so this is called the symmetric equations, and it plays again the role of an equation. It's a point tester. Okay, that's a good place to end it. Drawing the line right here. See y'all on Friday. Have a good one.
Yeah.
Yeah.